Let's continue on with our study of rotation of I guess functions around the x, and we'll soon see the y-axis as well. So let's do a slightly harder example than what we've been doing, but I think it might be obvious how to approach it. So there's my y-axis, there's my x-axis, and in a couple of I think it was 2 problems ago, we figured out if we had the function y is equal to square root of x. Let me try to draw it. So this is y equals square root of x. If we were to rotate that around the x-axis, what the volume would be between 2 points, let's say 0 and some other point. Now let's just pick an arbitrary point 1, and I think you know how to do that at this point. Now let's make it a slightly more difficult problem. Let's say I were to also draw the function y is equal to x squared. So that looks, if this is 1, they both meet at 1, right? Because the square root of 1 is 1, and 1 squared is 1. So that would look something like this. Something like that. They should be actually symmetric around y equals x. But anyway, so say y equals x squared looks like that. So my question now is, what is the volume if I were to take this figure and rotate it around? So what do I mean? So this area here, if I were to rotate that about the x-axis, what would the volume be? So now this is really, what we did just with the square root of x, we had like a solid cup, right? It would look something like this. It would be like a cup, and it was solid. We were just trying to figure out the volume of it. Hopefully that makes sense to you. Now it's going to be kind of a hollowed out cup, right? Because we have this inside function. And so the inside of the cup is going to be empty. Hopefully that makes a little sense. Remember, you're just taking this and then you're rotating it around the x-axis. Well, the way to think about it, especially if you're having trouble visualizing, actually the solution might help you visualize it. The volume of this figure, which I'm having trouble drawing, it will be the volume formed by the outside rotation, right, of, say, this, y equals square root of x. Let me do that in the yellow. Equals square root of x. It'll be the volume formed when that is rotated around, and the whole solid volume, minus the volume when minus this volume. Minus, so if we took the y equals x squared, right, y equals x squared would look something like that. And if you rotated it around the axis, try and draw it, it'd look something like that. I don't know if you've ever been to Morocco, but they have these tagine plates that the tops look a lot like that. Well, you probably have. Well, anyway, it would look something like that. So if we subtract out this volume when it's rotated around from the volume of y equals square root of x, when that's rotated, we'll get this figure that we're trying to figure out, this area when it's rotated around. And that should be intuitive for you, hopefully, because when we just did area under a curve, that's how we would figure out the area of this green area. We'd figure out the area under square root of x, and we'd subtract out the area under y equals x squared. That's y equals x squared. This time, we're going to say the volume of the revolution of y equals square root of x minus the volume of the revolution of y equals x squared. So let's do the problem. All right. So the total volume. Let me do a good color. Looks good. The total volume is going to be equal to the volume formed when we rotate y equals square root of x around the x-axis. And I said from 0 to 1, and that's because I picked where they meet. Sometimes in a book or on an exam, they'll just say, oh, the area between y equals x squared and y equals square of x, we're going to rotate that around, and you have to figure out, well, they intersect at 1, and you can just set the equations equal to each other to figure that out. We're going from 0 to 1, because they also intersect at 0. 0 squared is the same thing as square root of 0. We're going from 0 to 1. And so what's the volume of the larger, or I guess the y equals square root of x rotated around? I always forget the formula, so I always redraw a disk. So if that's the radius of my disk, the disk is going to come around like that. So we know that the radius is the function, right, of the disk. That's, of course, the dx is the depth of the disk. So the radius is the function, which for the outside one is square root of x. Square root of And we know area of this disk is pi r squared. So we square the radius, take a pi outside, and then we multiply that times the width. So that's where we get our dx. And of course, we sum them all up, and that's where we get the integral. And then I'm going to do it as two separate integrals. Some people will put them both within the same integral, but I really want to hit the point home that this is the volume of the kind of outside surface formed by the outside surface, or the cup, minus the volume formed by the inside function. This is going to be minus pi. It's still going to be from 0 to 1. I drew fairly huge integral signs. I don't know why. And what's the inside function? It's x squared, right? And that's going to be the radius of its own disks, right? If that's the radius, that's the disk. Dx is the width. So it'll be x squared times dx, right? So let's see if we can figure that out. So volume equals, let's take the pi's out. I think you'll see that pi is applying to everything, so we can take a pi out. And then times the integral. And now we can merge them back because, integrals are additive like that. Well, you'll see what I'm talking about. This integral is the same thing. So what's square root of x squared? Well, that's just x. And what's x squared squared? That's x to the fourth, right? You multiply the exponents, exponent rules. We have a minus sign here. Minus x to the fourth times dx. We have that pi on the outside. That equals, let's keep our pi on the outside. We're going to have to evaluate the antiderivative at 1 and 0. So what's the antiderivative of x? Well, it's x squared over 2. X squared over 2 minus, what's the antiderivative of x to the fourth? What's x to the fifth over 5? It's hopefully second nature to you. X to the fifth over 5. And we're going to evaluate that at 1 and 0. 1 and 0. We're going to subtract them, right? Fundamental theorem of calculus. So that equals, I'm going to switch colors to avoid monotony. That equals pi times, let's evaluate it at 1. So it's 1/2 minus 1/5. 1/2 minus 1/5. When you evaluate at 0, it's 0 minus 0. So when you evaluate 0, you get nothing. And so what's 1/2 minus 1/5? That's pi times, let's see, common denominator of 10. 5 halves is 1/2 minus 2 tenths is 1/5. So this will be 3. So we get 3 pi over 10. That's the volume formed. So it's almost easier to figure out the volume of this figure than to draw it. Anyway, I think I'll leave you there in this video, and in the next video, we're going to start rotating around the y-axis. See you soon.